What's up, everybody? Got another video here for you. This is business calculus optimization. It's actually two sections in this book. Covers optimization. This one has some optimization problems. Talk about absolute extrema, and then we talk about elasticity of demand and that kind of stuff. And then the next section, it gets into more optimization problems. So I'm doing this in two videos because it's split up into two sections in the book. So if you want to see all about optimization for the business calculus, watch this video and watch the video after this one. Okay. I'll label it something like additional optimization. Okay. And then I also have more optimization problems that I'll put the links to those videos in the description. It's just more optimization problems work from business calculus. They're just individual problems, like one problem per video. I'll post the links to those so you'll get even more examples in practice. So let's go ahead and get started. So how to find the absolute extrema of a continuous function f on a closed interval AB. So the first thing we do, we find all critical numbers of f on the open interval AB. So we want all the critical numbers that are between A and B. We remember how to do that. That's where you find the first derivative, set it equal to 0, and solve for x. And then compute f of x at the critical numbers from step 1 and at the endpoints A and B. So once you find the critical numbers, you're going to take the critical numbers, you're going to take the endpoints, and you're going to plug them back into the original function. And then the largest and smallest values from step 2, from what we just did, are respectively the absolute maximum and absolute minimum values of f of x on the closed interval AB. So let's work some examples and see what we've got here. So it says find the absolute maximum and absolute minimum of the function. So we've got this function on this interval. All right, so let's go ahead and find the derivative. So we've got f prime of x is equal to 6x squared plus 6x minus 12. And then we set this equal to 0. And we can divide everything by 6, make it easier for us to factor. And so we get x plus 2, x minus 1, so x plus 2 equals 0, or x minus 1 equals 0, so x equal negative 2, or x equal 1. So we can actually cross this one out. And why can we cross that one out? Because 1 is not between negative 3 and 0. That's the only numbers that we're looking at. Okay, so we have x equal negative 2, we've got negative 3, and we've got 0. Because remember, that's what it said. It says evaluate the function f of x, so the original function, at the two endpoints, negative 3 and 0, and at the critical numbers, negative 2. Well, the critical numbers that are in this interval. All right, so let's see what we've got. We've got f of negative 3 is equal to 2 times negative 3 cubed plus 3 times negative 3 squared minus 12 times negative 3 minus 7. That is going to give us 2 as an answer. And then we've got f of negative 2, which is 2 times negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2 minus 7. And that's going to give us an answer of 13. And then f of 0, that's going to give us 2 times 0 cubed plus 3 times 0 squared minus 12 times 0 minus 7. And that's going to equal negative 7. So we can say that we have an absolute minimum at, well, this is the smallest one, right? That's the smallest value we have. at 0, -7. See, the x was 0, the y was -7. And we have an absolute maximum at, well, which one's the largest? Where it equals 13. So at -2. At -2, 13. And there's your answer. All right. All right. Now, let's look at this one. It says, for several weeks, the highway department has been recording the speed of freeway traffic flowing past a certain downtown exit. The data suggests that between 1 and 6 p.m. on a normal weekday, the speed of the traffic at the exit is approximately this function here, this miles per hour. So that gives us S of t equals t cubed minus 10.5 t squared plus 30t plus 20, where t is the number of hours past noon. So past noon, from however many hours you are past 12 o'clock. At what time between 1 and 6 p.m. is the traffic moving the fastest, and at what time is it moving the slowest? All right. So we've got S of t is this, and we know that t is going to be between 1 and 6 because that's the interval that they're looking at. At what time between 1 and 6 p.m. Okay. So 1 o'clock is 1 hour past noon, so t would be 1, and 6 p.m. is 6 hours past noon, so t would be 6. So we're looking between 1 and 6. All right, so let's take the derivative. So we've got S prime of t is 3t squared minus 21t plus 30. And then we're going to take this, set it equal to 0. So we've got 3t squared minus 21t plus 30 equals 0. We can divide everything by 3. So t squared minus 7t plus 10 equals 0. So t minus 5 times t minus 2 equals 0. So we get t equals 5 or t equals 2. All right, so now to find the absolute max and min between those times, we've got to evaluate the function at 5, 2, 1, and 6. See, the 5 and the 2, they both fall in this interval, so we evaluate all of those. So we have f of 1. Okay, so all I'm going to do is I'm going to replace the t with a 1 here. Okay, so just remember the f of 1, the f of 2, f of 5, and f of 6. Now I'm not going to write all this out, but I'm taking each one of these values and plugging them into this original function here. And when you do that, you get 40.5, you get 46, you get 32.5, and you get 38. All right, so we can see moving fastest at when? Well, that's right here. See, that's the largest value, 46. So moving fastest at 2 p.m., okay, and its speed is 46 miles per hour. And then it's moving slowest at, well, which one's the smallest? That's this one. That's the 32.5. At 5 p.m., probably because everybody's getting off work, and the speed is 32.5 miles per hour. And that's what they were asking us. All right, so that's pretty neat. All right, let's look at this one. All right, so it says, when you cough, the radius of your trachea decreases, affecting the speed of the air in the trachea. If R0 is the normal radius of the trachea, the relationship between the speed s of the air and the radius r of the trachea during a cough is given by a function of the form. So we've got s of r is equal to a times r squared times r0 minus r. All right. Where a is a positive constant. So a is a constant, and we know that r0 is a constant. R0 represents the normal radius of your trachea. Find the radius r for which the speed of the air is greatest. All right. So this is an absolute max min. So we know that the radius of our trachea is going to be between 0 and then what? Well, let's think about it. It says R0 is the normal radius of the trachea. Okay, so remember, when you cough, your trachea is decreasing. So it's not going to be any larger than the normal size. So it's going to be between 0 and R0. All right, so let's go ahead and find the derivative. So I've got s prime of r. Now this is a product rule. So remember, this is we'll call this our first function, and then this will be the second function. So it's the derivative of the first function times the second function plus the derivative of the second function times the first function. So the derivative of the first function is 2ar. Remember, a is just a number. So that's the derivative of the first times the second plus the derivative of this one. Well, r0's a constant, so derivative of that is 0. Derivative minus r is -1, and then times ar squared. And so this is going to be 2ar times r0 minus r minus ar squared. And so I get s prime of r is equal to, let's do ar times 2 times r0 minus r minus r. I just factored out a common factor of ar. And so when I pull that out of here, I'm left with 2 times this. And when I pull an ar out of this, I'm left with just the r. And so this is going to be ar times 2r0 minus 2r minus r. So s prime of r is equal to ar times, and that's going to be 2r0 minus 3r. So there's our derivative. So now we've got to take this, set it equal to 0, and let's do them running out of room. So I've got ar, now let's do it right here. We've got ar times 2r0 minus 3r equals 0. So ar equals 0, or 2r0 minus 3r equals 0. So here I get r equals 0. Here I get 2r0 equals 3r. So r is 2/3 r0. All right. So now, well, what do we have to do? We have to evaluate s of r at 0, r0, and this value. And notice one of our critical numbers is an endpoint. All right, so this, when I plug the r in, well, let's plug the 0 in first. So that's going to give me a times 0 squared times r minus 0, which is 0. And then s of 2/3 r0, that's going to be a times 2/3 r0 squared times r0 minus 2/3 r0. All right, so let me just come up here. Let's see. I'm going to come down here work this out. Let's see, so that's going to be a times 4/9 r0 squared times times, well, that's 1 r0 minus 2/3 r0, that's 1/3 r0. And so when I multiply all of that, that is going to be 4, let's see, 4 r0 cubed. Let's just go ahead and stick the a right here. 4a r0 cubed over, what is that, 27? All right, so that's going to be 4a r0 cubed over 27. And then if we do s of r0, that's the other endpoint. Well, you can see that's going to give me 0. A times r squared times r0 minus r0, that's 0. So that's going to give me 0 there. Okay. So it's greatest when r is equal to 2/3 r0. This is going to be your largest value. See, both of those are 0. And so there's your answer. All right. That wasn't too bad. All right. So here we've got if the exist. That probably should say if it exists, find the absolute maximum and absolute minimum of the function f of x equal x squared plus 16 over x on the interval x greater than 0. All right. So let's see what we've got here. Well, let's take the derivative. So f prime of x is equal to 2x minus 16 over x squared. Okay. So let's talk about this negative 16 over x squared real quick. All right. So if you have 1 over x and you want to take the derivative of that, that derivative is just, so just forget about the problem right now. I'm just going to show you this. So if you have f of x equals 1 over x, and if you want to take the derivative, you would write that probably what? X to the negative 1. So f prime of x is equal to negative 1 x to the negative 2, which is negative 1 over x squared. Okay? And look, if you had f of x equals, say, some number c, a constant c over x, and you want to take the derivative, well, you would write f of x equals cx to the negative 1. So f prime of x would be negative c x to the negative 2, which would be negative c over x squared. So what I'm getting at is if you're taking the derivative of 1 over x, it's just negative 1 over x squared. If you're taking the derivative of some number over x, then it's minus that number over x squared. See? So just remember that'll keep you from having to go to the side like I did here and doing that. And you know, if you don't remember that the derivative of 16 over x is negative 16 over x squared, just go off to the side and do it using the power rule. Okay. All right, so let's go ahead, set this equal to 0. And so I get 2x equals 16 over x squared. Cross multiply, so, and then we can go ahead and divide by 2, so that gives me x cubed equals 8. So x equal 2. All right. So notice x is going to infinity. This is, there's really no, there's no endpoints, I guess you could say, because it's going to infinity. And then, I mean, it doesn't equal 0. So, I mean, we can get close to 0, but that's infinite there, right? Because if you give me if you give me a number closer to 0, I can always get just a little bit closer. Okay, so when we look at this, we look at the 2 here, and say if I choose x equal 1 and x equal 3, and I take the 1 here and I plug it in to the derivative, then I get 2 minus 16. That's negative, right? So that tells me here it's decreasing. And then if I do f prime of 3, I plug the 3 into here. Well, you can verify it, but when you plug the 3 in, you're going to get a positive number. So that's increasing. And so you can see I've got an absolute min at 2, right? At 2. And then I would need to know my y value. So f of 2 is equal to 2 squared plus 16 over 2. So that's just 4 plus 8, which is 12. And all I did is I took the 2 and I plugged it into the original function to get my y value. And then for an absolute max, that would be none. Because, I mean, think about it. As x goes to infinity, this thing just keeps increasing. It's increasing and then increasing. So we only have it right there at 2. All right. Let's look at this. We've got marginal analysis criterion for maximum profit. All right, so it says the profit P of Q is equal to R of Q minus C of Q. Okay, so the profit is just revenue minus cost, is maximized at a level of production Q where marginal revenue equals marginal cost and the rate of change of marginal cost exceeds the rate of change of marginal revenue. So basically what they're doing is they're telling you to find the marginal, or to find the maximum profit. You take the marginal revenue, set it equal to the marginal cost. So basically what you're doing is taking the derivative of the revenue and setting it equal to the derivative of the cost, and then solving for Q. And then to check that, if the second derivative of the revenue is less than the second derivative of the cost, then that means you have a maximum profit. Now there is a thing in here. I don't usually cover it that much. I didn't even put it in the notes here, but there is a second derivative test, and that's kind of like what we're looking at here. So you see up here how we determined there was a minimum here because it's decreasing and then it starts increasing, and so that would give us a minimum. Well, the second derivative test for absolute extreme, so, and I'll just go ahead and read it to you, and you can write it down if you want. It says, suppose that f of x is continuous on an interval I where x equals c is the only critical number, and that f prime of c is equal to 0. So you found your critical number. So if f double prime of c, so if we take the critical number and evaluate it in the second derivative, if that's positive, we have an absolute minimum there. And if the second derivative evaluated at your critical number is negative, then we have an absolute maximum there. Okay. All right, so let's see. Now we have marginal analysis criterion for minimal average cost. So the average cost is minimized at the level of production where average cost equals marginal cost. That is, we take the average cost and set it equal to the derivative of the cost function, the marginal cost. All right, and so the average cost is the cost function divided by Q. Okay. All right, so let's work some examples with this. All right, so it says you are given the price P of Q. That's a lowercase p. This is a capital P. So you are given the price P of Q at which Q units, Q represents how many units, of a particular commodity can be sold, and the total cost C of Q of producing the Q units. So in each case, find the profit function, the marginal revenue, the marginal cost, and determine the level of production Q where P of Q is maximized. And then find the average cost A of Q and determine the level of production Q where A of Q is minimized. So basically we're finding what we just went over here. Some examples here. All right. So let's find all this stuff. We're going to find the find the profit function. Well, in order to do that, we got to have the revenue and the cost function. They give us the cost function. So we actually need and this is part A, we need the revenue function. Well, that's just Q times the price, which is 49 minus Q. So that's 49Q minus Q squared. There's the revenue. So our profit function is revenue minus cost. Okay. And so let's see, we've got our profit function. So we've got -1 minus 1/8, which is -9/8 Q squared. And then 49Q minus 4Q is 45Q. And then minus the 200. That is a Q right there. All right. So there's your profit function. And that's the answer to one of them. And then we need the marginal revenue. So the marginal revenue, which is R prime of Q, that's going to be 49 minus 2Q. That's this, see, 49 minus 2Q. And then the marginal cost, that's the derivative of this. That's going to be 1/4 Q plus 4. Okay. All right. So there's the marginal revenue. There's the marginal cost. And then they want us to find the maximum profit. So remember, from up here, that tells you that's when the marginal revenue equals the marginal cost. And so if we take the marginal revenue, 49 minus 2Q equals 1/4 Q plus 4. So move this over. So let's see, 2 plus 2Q plus 2Q minus 4. So that's 45 equals, what does that equal? 8. Is that 9/4Q? I believe. And then if I multiply by 4/9, that's 5 times 4. Q is equal to 20. And then so if I do, and then I can show that it is maximum. So if we do R double prime of Q is equal to -2, and C double prime of Q is equal to 1/4. And so I've got I've got R double prime of 20, because that's what we found, 20, is equal to -2, and then C double prime of 20 is 1/4, and so we can see that -2 is less than 1/4. Remember, this is R double prime at 20, and this is C double prime at 20. And so what did we show? we showed that R double prime is less than C double prime. And so that means that Q equal 20 is where we would have our maximum profit. Okay. All right, let's look at part B. So part B tells us to find the average cost and then determine the level of production Q where A of Q is minimized. So our average cost, remember that's C of Q over Q. So our cost function is this right here. So that's 1/8 Q squared plus 4Q plus 200 over Q. So that would be 1/8 Q plus 4 plus 200 over Q. So there's your average cost. And so now they want us to minimize, find the minimal cost. So that is when the average cost is equal to the marginal cost. So we've got our average cost, which is 1/8 Q squared plus 4Q plus 200 over Q is equal to the marginal cost, which is this, which is 1/4 Q squared plus 1/4 Q plus 4. Now, I know what you might be thinking. Well, this is what you got for average cost. Yeah, this is what I got for the average cost, but I'm going to use this when I solve it because it's just easier to multiply through by Q. Just easier to solve it when it's in this form. So that's going to give me 1/8 Q squared plus 4Q plus 200 equals 1/4 Q squared plus 4Q. And you can see those go out. And so if I move this over here, 1/4 minus 1/8 would be what? 1/8. All right. So that is going to give us 200 equals 1/8 Q squared multiplied through by 8. So I get Q squared equals 1600. And so I get Q is equal to the square root of that, which is 40. And there's your answer. So, I mean, you can see it's not too bad. Okay. It's quite a bit of work, but it's not bad at all. All right. So let's work another problem like this. It's the same thing that we did. We got us a cubed here, so it might, a little bit different, but it doesn't hurt to work more than one of those types. All right, so we've got R of Q is equal to Q times 180 minus 2Q, which is 180Q minus 2Q squared. And then our profit is going to be our revenue, 180Q minus 2Q squared minus our cost, Q cubed, plus 5Q plus 162. And so our profit is going to be negative Q cubed minus 2Q squared. And then I've got 180 minus 5, so that's plus 175Q minus 162. So there's your profit. All right, and then we need our marginal revenue. So our marginal revenue, that's going to be R prime of Q will be, let's see, we're taking the derivative of this. So that's 180 minus 4Q. And our marginal cost is 3Q squared plus 5. All right, so there's your marginal revenue. There's your marginal cost. And then to maximize, we set those equal to each other. 180 minus 4q equals 3q squared plus 5. So I'm going to move the 180 and I'm going to move the 4q to this side. So I get 3q squared plus 4q minus 175 equals 0. All right. And then this will factor into q minus 7 times 3 plus 25. 3q plus 25 equals 0. So q equals 7 or q equals, and if I solve that, that's negative 25 over 3. So we know it's not the negative. And so that's q equals 7. All right. Now we need to test this out. So I've got r double prime of q is equal to negative 4 and c double prime of q is equal to 6q. So r double prime evaluated at 7 is negative 4 and c double prime evaluated at 7 is 42. And we can see that r double prime is less than c double prime evaluated at 7. And so that tells us, remember back from up here, if the revenue's less than the cost, the second derivative of the revenue is less than the second derivative of the cost, then that's your maximum profit. Okay, so there's that, and this was part A. Now let's do part B. So we need average cost. So the average cost, which is C of Q over Q. So our cost function, there's our cost function. That's going to be Q cubed, Q to the third, plus 5Q plus 162 plus 5Q plus 162 over Q, which is Q squared plus 5 plus 162 over Q. So there's our average cost. And so remember, to find the minimum, we take the average cost. So let's take the Q to the third plus 5Q plus 162 over Q and set that equal to the marginal cost, which is 3Q squared plus 5. 3Q squared plus 5. It's just easier to solve this one than this one. That's the only reason. Just easier to solve. And so that is going to be Q raised to the third plus 5Q plus 162. And if I multiply the Q, that's 3Q to the third plus 5Q. Well, you can see those cancel out. And I'm going to be left with 162 equals 2Q to the third. Divide by 2. That's going to be Q to the third equals 81. And so here we're going to get Q is equal to the cube root of 81. That is a Q, which that ends up being 4.327. All right. All right. So far that's not too bad. All right. Let's look at this. All right, price elasticity of demand. If Q is equal to D of P units of a commodity or demanded by the market at a unit price P, where D is a differentiable function, then the price elasticity of demand for the commodity is given by E of P is equal to P over Q times the derivative of Q with respect to P, and has the interpretation percentage rate of change in demand Q produced by a 1% rate of change in price P. I'll explain that more while we're working the examples. Okay, you'll understand this better while we're working the examples. And then I have levels of elasticity. If the absolute value of E of P is greater than 1, we have an elastic demand. The percentage decrease in demand is greater than the percentage increase in price that caused it. Thus, demand is relatively sensitive to changes in price. And if it's less than 0, it's inelastic demand. The percentage decrease in demand is less than the percentage increase in price that caused it. Thus, demand is relatively insensitive to changes in price. And then if it's equal to 1, demand is of unit elasticity or unitary. The percentage changes in price and demand are approximately equal. And then we have levels of elasticity and the effect on revenue. If demand is elastic, where the absolute value is greater than 0, revenue, R equals P times Q of P, decreases as price P increases. Okay, so revenue decreases as price increases. And if it's inelastic, revenue increases as price increases. And if demand is unit elasticity, where it equals 1, revenue is unaffected by a small change in price. All right, so that's something you just need to know that. Okay, you've got to know that. So let's look at an example. I think these next examples will kind of clear up what all of this right here means. Okay. Suppose the demand Q and price P for a certain commodity are related by the linear equation this. A. Express the elasticity of demand as a function of P. Calculate the elasticity of demand when the price is 100. Interpret your answer. When it's 50, interpret your answer. And at what price is the elasticity of demand equal to -1? What is the economic significance of this price? All right. So, it's good to know how to solve these things. But we've also, so we got Q is 240 minus 2P. 240 minus 2P. And we've got P is between 0 and 120. But we've also got to understand, not just solve them, we've got to also know, well, what are we finding, right? All right, so let's find the elasticity of demand. So remember, that's P over Q times the derivative of Q over, derivative of Q with respect to P. So first, let's come over here and find dQ dP. Well, that's just -2, right? And so here we get E of P is equal to P over Q. Well, what's Q? Q is 240 minus 2P times the derivative, -2. And so this tells us we get E of P is -2P over 240 minus 2P, which tells us that E of P is equal to -P over 120 minus P. So all I did, 2 goes into each one of those. Okay, so that's part A. Part B, they want us to evaluate it at 100. So we take the 100, plug it in, so that's -100 over 120 minus 100, which is -5. All right. So what does this mean? This goes back to the stuff that we read up there. So what this means is when P is equal to 100, a 1% increase in price produces a decrease in demand of about 5%. So we got a -5 there. Okay. So if we increase the price by 1%, that's going to decrease the demand by about 5%. Okay. I'm not going to write that out. You can play it back if you want to write it out. And then we've got E of 50. So that's going to be -50 over 120 minus 50, which that is about, plug that into your calculator, you get -0.71. All right, so what does that mean? Well, it's the same thing as before. A 1% increase in price produces a decrease in demand of about 0.71%. Okay, and that's what it means. All right, so part D. At what price is the elasticity of demand equal to -1? What is the economic significance of this price? So what we're doing here is we're taking the elasticity of demand and we're setting it equal to -1. So that's -P over 120 minus P, which we multiply through by, well, let's just do this. That's 1 equals P over 120 minus P, multiplied through by -1. So that's going to be 120 minus P equals P. So 120 equals 2P, which tells us that P is equal to 60. So what does that do? Well, at the price of $60, a 1% increase in price will result in about a 1% decrease in demand. Okay? That's all that means. All right, let's look at some more problems. All right, so this is going to be, I guess, similar to the one we just worked. All right, compute the elasticity of demand for the given demand function D of P and determine whether the demand is elastic, inelastic, or of unit elasticity at the indicated price P. All right, so basically what we have here is we've got Q is equal to 3,000 over P minus 100. So if you remember back up here, notice the D of P, I changed it to a Q. But if you look up here, Q is equal to D of P. It's just easier to work with it when it says Q equals. And then, we're going to take the derivative dQ with respect to P. Derivative Q with respect to P. All right, so let's find that. So we've got D of Q, or derivative Q with respect to P. That's going to be, now what is that? Remember what I told you earlier? That's -3,000 over P squared. Okay? And so I've got E of P is equal to P over Q times derivative Q with respect to P. So that's going to be P over Q, which is 3,000 over P minus 100, times the derivative, -3,000 over P squared. All right, so how do we simplify this? So basically what we can do is we can multiply each one of these terms by P. See that? Multiply each one of them by P. And so that's going to give me P squared over 3,000 minus 100 P times -3,000 over P squared. And so this is going to give us, see how the P squareds cancel? That's going to be, what is that? -3,000 over 3,000 minus 100 P. That's a 3 right there. Let me. All right. And then 100 goes into each of these. That's going to be negative 30 over 30 minus P. And then if I take this negative, I can take this negative and distribute it down here. And so that's going to give me E of P is equal to 30 over, and if I distribute the negative 1 down here, that's going to be P minus 30. Okay? I mean, you don't have to do it like that, but I mean, that's what I did. And so we want to do E of 10, right? E of 10. And so that's going to be 30 over 10 minus 30, which is 30 over negative 20, which is negative 3/2. And so if we do the absolute value of E of 10, that's the absolute value of negative 3/2, which is 3/2, which that is larger than 1. Okay? So what does that mean? So if I take the absolute value and evaluate it, and I got a value larger than 1, that means it's elastic demand. So this is elastic. Whoop. And that's all they were asking you to do there. Determine whether the demand is elastic, inelastic, or of unit elasticity. Okay. We're going to work some more problems like this. Actually, this right here, okay, we're on our last problem now. This is it. All right. So this is going to be kind of similar. This is going to be similar to the problem we just worked. We'll do a little more detail with it. All right, so the manager of a bookstore determines that when a certain new novel is priced at P dollars per copy, the daily demand will be, so this is part A, Q is equal to 300 minus P squared copies, where P is between 0 and the square root of 300. Determine where the demand is elastic, inelastic, and of unit elasticity with respect to price. All right. So we've got to find the elasticity of demand, and then we want to see, well, when is it elastic, inelastic, and unit elasticity. All right, so, well, we know we're going to need the derivative of Q with respect to P, which is negative 2P. And so we get E of P is equal to P over Q times derivative of Q with respect to P. So that's going to be P over 300 minus P squared times the derivative, that's negative 2P. So that is negative 2P squared over 300 minus P squared. Okay. All right. And since we have P between 0 and square root of 300, okay, so let's think about this. Between 0 and square, obviously for this it's not going to be able to equal 300 because that would give us a 0 in the denominator. See right here? But notice whatever number we plug into here, that's going to be positive down here, and this up here, just the 2P squared, that's positive. So the positive over positive is a positive, but then it's going to be, but then I've got the negative sign. So what I can say is that the absolute value of our elasticity of demand is going to be 2P squared over 300 minus p squared. I can just get rid of that negative sign because see here, this part right here, that's positive. That's always positive. So the absolute value would be just without that negative sign. All right. Okay, so it wants us to determine when it's elastic, inelastic, and unit elasticity. So remember, unit elasticity. So unit elasticity is when what? When it's equal to 1, right? That's from, I know I'm going to come back up here. See, unit elasticity is when it's equal to 1. All right. So we're going to take 2p squared over 300 minus p squared equals 1. So that means 2p squared equals 300 minus p squared, which means 3p squared equals 300. So p squared equals 100. So p is equal to plus or minus 10 when you do the square root of it, right? But we know it's going to be p equals 10 because 10 is the one between, where is it? Between 0 and square root of 300. But do remember that when you do square root both sides, it's plus or minus. You're using that square root property. And so there we go. That's when it's unit elasticity. Now let's look if, okay, so if p is between 0 and 10, okay, so remember we're up here, we are between, let me just write this over here. Well, let's write it down here. 0 less than or equal to p less than or equal to square root of 300. That's the range we're looking for. And we know it's unit elasticity at 10, right? And so we would have the absolute value of E, okay, of our E of P, which is equal to 2p squared over 300 minus p squared is less than 2 times 10 squared over 300 minus 10 squared, which equals 1. Okay, so when p is between 0 and 10, it's going to be less than this. Well, I kind of messed that up a little bit. That should be less than 10, not less than or equal to. So when p is between 0 and 10, our elasticity of demand will be smaller than what it is evaluated at 10. Okay, so what I'm doing is I'm saying, okay, if I take a p-value from 0 less than 10, okay, between 0 and 10, but not including the 10, and I plug it into here, I'm going to get a value less than from up here, if I plug the 10 in. Because see, if I plug 10 in, that gives me 1. But if I plug something smaller than 10 in, that's going to give me a value less than 1. And what happens if the absolute value of E is less than 1? That means it's inelastic. Okay, so that's from 0 to 10. So remember, when the absolute value of E is less than 1, let me go back up here again, it's inelastic. And when it's greater than 1, it's elastic. All right, so let's look at this. So now we have if, let's see, we're going to have 10, all right, less than P less than equal to 300. Nope, I'm sorry. Keep putting that equal sign down there. less than 300. So it's if it's from 10 to 300, then the absolute value of E equals 3p squared. Not 3. 2p squared over 300 minus p squared, which that would be, so if I plug in a number like 11, 12, 13, so on, that's going to be greater than if I plug the 10 in, which, remember, that's going to give me, see, this is equal to 1. But if I plug one of these values in between 10 and square root of 300, not including those numbers, that's going to give me a value larger than 1. And so that means it would be elastic from 10 to square root of 300. Okay. So I guess this right here is what they were wanting you to find. Okay. All right. And then part B, interpret the results of part A in terms of the behavior of total revenue as a function of price. All right. So basically what this means is the total revenue, where R equals PQ, increases when demand is inelastic. That is, so for this one, when we are between 0 and 10, because it's inelastic, the range of prices for this range of prices between 0 and 10, a percentage increase in price results in a smaller percentage decrease in demand. So the bookstore will probably take in more money for each increase. Well, it will take in more money for each increase in price up to $10 per copy. But for the price range 10 to square root of 300, the demand is elastic, so the revenue is decreasing. And if the book is priced in this range above $10, a percentage increase in price results in a larger percentage decrease in demand. So if the bookstore increases the price beyond $10 per copy, it will lose revenue. And so the optimal price per copy would be the $10. Okay. And that right there, what I explained there, that goes back up here to this right here. All right. So there you saw it applied there. All right. But yeah, that's the video. And like I said, the other video for optimization, that's a separate video, and it's probably going to be just as long as this one. That's one of the reasons I split it up like I did, and for the simple reason that the book split it up. But watch both videos, you'll get an entire lesson on optimization. All right, a good lesson on optimization. And don't forget to check out the extra problems in the description. And if I forget to put those links in the description, somebody just leave a comment saying, hey, put the links to the single optimization problems in the description. All right. Well, I hope you enjoyed this. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.